Let's move on now to creating formation models, and we'll start off with doing this for exoplanets. And so we're going to break this into two parts. We're going to start off with models designed to reproduce the population of close-in super-Earths or sub-Neptunes. And then as a second part, we'll talk about giant exoplanets, gas giants. So just as a recap, remember this is the population of exoplanets that we've detected so far. And again, this is not perfectly up to date, but these kind of general populations are still, they still hold. And so the super-Earths are, of course, this population of mostly red points, kind of close to their stars at sizes or masses that are a little bit bigger than Earth. And as we talked about, most, I shouldn't say most, about a third to a half of all main sequence stars are thought to have super-Earth planets around them. And so they're kind of a key population of objects that we would like to understand. All right, these guys right here. They're a little bit closer in and a little bit, on average, a little bit bigger than Earth. And we want to know what's up with them. So here's a graph just kind of showing systems that have several super-Earths with the solar system for comparison at the bottom. And so what you can see here is the x-axis of this plot is very spread out. All right? So you can see things going from very close to the star out to Earth's orbit. And you can see the solar system at the bottom for scale. Okay? And what you can see is systems that have more than one super-Earth often have several, and they look very close together on this plot. You know, what does that really mean? Well, since this is a logarithmic plot, the distance between any 2 points, any two planets, basically represents a ratio of orbital periods. Okay? And so the orbital period ratio of the inner one to outer one. And so we can compare the separation between super-Earths in terms of period ratio with those in the solar system. And as you can see from the solar system at the bottom, even though the solar system planets are further out, kind of the Earth-Venus orbital period ratio is not that different from what we see for many of these super-Earth systems, which is kind of interesting. And so again, this leads us to this period ratio distribution. So I mentioned this in passing in the last talk. And so here, let me just kind of explain it a little bit more. So what this distribution is showing is basically taking all systems of super-Earths where there's more than one planet orbiting the same star, then taking the ratio of orbital periods of every pair of neighboring planets and chucking those in a box or a bucket or whatever you want. And then that's this distribution, okay? So that's the period ratio distribution. A way that's, I think, a little bit more informative to look at it is as a cumulative distribution, right? And so when you look at it like this, you can see this kind of smoothish curve going from 1 to 3 or so. What does this tell you? And what's most interesting, I think, about this distribution is actually not what it looks like. It's what it doesn't look like. It does not look like a staircase. And a lot of people expected this sort of distribution to look like a staircase. And the reason is that we think that orbital resonances, mean motion resonances between planets, there's good reason to think that maybe they should be very common. And if they're common, resonances happen when there's kind of a ratio of integers of 2 orbital periods, like 3 to 2, or 2 to 1, or 4 to 3. Right? And so if most systems were in resonance, we would get a staircase function instead of this smooth thing. And that's a very key piece of information. So kind of this red staircase that I've drawn on there by hand is assuming that among all pairs of planets, half of them were in a 3 to 2 orbital resonance and half were in 2 to 1 orbital resonance. Okay? If that were the case, then the distribution would be that red staircase. But it's not. It's that gray line. Right? This is key information. So now let's talk about formation models for these close-in, slightly larger than Earth-sized planets. Now, in a conceptual way, you can say, okay, in terms of size on the y-axis or mass and orbital distance on the x-axis, let's say super-Earths are up there. They're this gray box up there. So how do planets get there? Just from a very simple conceptual point of view. Well, there's many different ways that you can imagine this happening. One is, well, they just grew where they are. The things bashed together and grew bigger planets where they are now. All right? And that's what we call in situ accretion. Right? Another idea is maybe they grew mostly where they are, but there was not enough stuff there originally, and so the kind of their material was supplemented by small objects that drifted inward from further out. So this would be kind of like the pebbles we talked about last time, drifting inward, but then getting concentrated close to their stars, having enough stuff to grow planets close in. All right, and I'll call it the drift model. The other idea is that, well, maybe larger things move inward, and it's large objects like planetary embryos or almost full-size planets that grow mostly further out, but then migrate inward at large sizes. Okay? So that's the migration model. And as we will see, both the drift model and the migration model are pretty plausible, and the in situ model is not. And so the reason that those curves happened at kind of very small sizes and very big ones, the inward drift of material, either as the size of pebbles or as the size of, large planetary embryos, is because of how fast things drift. And again, we talked about this a little bit last time, because of a headwind between small growing objects and the gas, things that are small can drift inward because of aerodynamic drag. And large things can go inward because of migration. And in between, things don't go that far, or that fast, I should say. And so kind of the typical size scales where we think processes make objects spiral in quickly are things at like pebble size and, objects that are more or less, as big as Earth or so. And so that's why there's these two models kind of at either small sizes or big sizes and not everything in between. At least we don't. What else do we know? Well, we know that the growth time scales very close in are very short. So this is showing an animation of a population of rocky stuff that was basically just thrown close to a star, and we're going to see it collide and grow and see how long that takes. Okay? And the y-axis here is the eccentricity, the orbital eccentricity, how stretched out an orbit is, and the x-axis is the orbital radius, the semi-major axis. And so here we go. And so boom, things are moving along, things are sweeping into each other, bashing into each other. And you can see within, a few thousand years even, the planets that were very close in were basically fully grown. And within, 100,000 years or so, basically the planet formation is over. And you can see here the masses of the planets at the end, they're all a few Earth masses or whatnot. And so what does this tell us? It basically tells us that the action close in happens fast. It's not a big surprise, but this is just kind of to demonstrate it. Right? Things grow really fast close to their stars. Yet, remember, this is all happening in the context of gaseous disks. And so remember, gaseous disks, as we saw last time, they don't last that long. They last a few million years. Right? So growth happens really, really fast in thousands of years or maybe 100,000 years. And yet gas disks last a lot longer than that, many millions of years. So what does that mean? It means that there must be time for these growing planets to interact with the gaseous disk. And so this graph is showing basically a simple measure of a migration time scale on the y-axis as a function of distance. And each of those dots is one super Earth planet. And I kind of made some simple assumptions about what the gas disk looked like to calculate a migration time scale. So we know these planets, if they formed where they are, would form really fast. And what this plot shows is that if they form where they are while there's still gas there, they should migrate really fast. And so basically this just means that we can't ignore migration. So the idea that planets form in situ, that first curve where planets just grow where they are without worrying about things moving around, cannot make sense. And simply because of timescales. There's just, things grow fast, they have to interact with the gas, which means that they have to migrate. Right? So in situ by itself just doesn't make sense. All right? Boom. Sorry, in situ growth is impossible. You have to include migration within the story. It has to be a part of the story. And you get to decide how big a part, but it has to be part of the story. So let's think about, this general picture again. We're going to go back and rewind a little bit just to kind of put the planet formation pieces kind of in a context again. So here's again a nice, simple, gaseous planet-forming disk around a young star. So the first stage of planet formation, as we talked about, is pebbles growing and bashing into each other and drifting until they find a place where they have a sufficient concentration to concentrate a little more, and then by the streaming instability, concentrate a little more, and then clump directly to form planetesimals. Okay? This is kind of a recap of what we talked about last time, but you get the idea. So we think planetesimals form. Then they undergo a process where they bash into each other, and they can also grab onto pebbles. And we talked about pebble accretion already, so I'll go through it pretty quickly. But these are kind of the prequels to what's going on, the real action in the super Earth story. All right, and once there's a population of planetesimals, again, we don't know exactly where and when they form, but they may form throughout the disk. Those that are close to the star are probably pretty rocky, and past the snow line where the temperature is cold enough that ice can be used as a building block, then they can contain some ice as well. And so remember, there's still pebbles that are drifting along here, and by pebble accretion and planetesimal accretion, that is a lot faster out past the snow line, out where ice can be a building block. And why is that? We think that it's actually because pebbles are probably bigger. Instead of being individual little bitty dust grains, or little grains of sand kind of thing as pebbles, past the snow line, they're more like grains of sand that are all kind of a few grains of sand stuck together with some ice. And so we think they're kind of clumps of many of these. And these pebbles being a little bit bigger translates into a much faster growth rate. And that's why, according to models, in the time it takes rocky planetary embryos to grow to, say the size of the moon or Mars, out where ice can be used as a building block, they're more like 5 or 10 Earth masses. Right? And so this is kind of a typical picture of how we think things grow, and it's nice. It's a nice cartoon version of the solar system too, right? Where we have small things close to the sun and big things further out. But we're not talking about the solar system. We're talking about systems that look totally different. Right? And so another possibility is that in this whole picture, after planetesimals grow, as we talked about, pebbles are drifting inward all the time. Well, what about the pebbles that don't grow into anything? Do they just go away and disappear? Well, maybe they actually get trapped. And so this drift model proposes that those pebbles that drift inward, that don't end up building other stuff, don't just disappear or sublime or evaporate away. Instead, sometimes maybe they can get trapped and maybe there can be a concentration of them close to the star because of a pressure bump in the disk close to the star, or some other reason that would concentrate those instead of letting them go to waste and grow them into something. I mean, it would be like just grabbing lots of leftover stuff and using it for something useful, like making something artsy out of trash you find on the street. Right? So maybe during the time it takes for large planetary cores to grow out past the snow line, there's a few really big, massive ones that can form close to stars, at least sometimes when there's the conditions that are right to trap these growing pebbles. And so both of those stories are kind of equally plausible for now. The idea that some large things could grow close to the star is possible, and the details are being worked out now. The idea that big ones should grow faster further out is also being thought about now, and it depends on things like where planetesimals form first, and exactly what the structure of the gas in the disk looks like. And those are also being worked out now. So it's a kind of a moving target, but the pieces of the story are kind of coming together. Regardless of exactly where they form, all roads lead to migration. And so why do I say this? It's basically because, as I said before, the time scales are such that things grow fast, and they have to grow much faster than the time scale for the gas to go away. And so there has to be a window where large planets are interacting with the gaseous disk. And when they do that, they do, like we saw before, they launch spiral density waves in the disk, and those spiral density waves torque the planet's orbit and cause it to shrink or grow. And in the case of planets that are going to end up on very close-in orbits, we think that the orbits mostly shrink to get there. Okay? And remember, this happens for planets that are more massive, roughly, than Earth, and more massive things migrate a little bit faster. And of course, the final ingredient here that we also talked about a little bit is that migration does not cause planets to just fall on their stars. Rather, they get trapped at the inner edge of the disk. And we think there really are inner edges to these disks. And so, going back to the story, starting from a distribution where there's relatively small rocky planetary embryos close to the star and bigger planetary cores forming further out, we think that migration should do something like this. It should make the big guys especially migrate inward through the small guys towards the inner edge of the disk. And as you have already seen, because I already played the animation, this does not cause all of the planets to just kind of clump up into one big one. Instead, what happens systematically in migration is that planets find kind of little stable spots. And these stable spots correspond to orbital resonances. And so here I've kind of labeled, just by hand, the typical types of orbital resonances we see in simulations of this process. We tend to form long chains of super-Earths that are all in each pair of neighbors is in resonance with its neighbor. And the resonances can be things like 4 to 3, or 3 to 2, or 2 to 1. Those kinds of resonances are very common in our computer simulations of this process. And basically, this evolution generically leads to these long resonant chains where the innermost planet or planets are kind of close to the inner edge of the disk, and then all the other planets are stacked up on there, and each pair is in resonance. And you might think, well, as we saw before, we don't have a staircase. The period ratio is not a staircase. This is obviously not what happens. And to that, I would say, just wait a moment, because the story is not over, right? This is happening while the gas disk is there. The gas disk caused the migration to happen, and the gas is still there. The gas is not there now. So what happens as the gas disk goes away? I like to describe the gas disk as being kind of like a teacher that keeps the kids in line. And so at recess, if there's a teacher, at least if the teacher is, strict, then the teacher can keep the kids in line and make sure they're not doing anything too stupid. And as soon as the teacher leaves, then boom, the kids go crazy, right? And it's the same deal with resonant chains. Resonant chains are like the plants are like the kids, and the gas is like the teacher. As the gas goes away after a few million years, what usually happens is that the systems of planets go unstable, and there's kind of a final phase of collisions. All right, basically the system goes unstable as the gas goes away, and that destroys the resonances. It spreads out the systems, and so this works surprisingly well when you look at this period ratio distribution again. And so again, this is that curve where it's like, what's going on here? And now let me show you two other plots. The one in red, that curve are those resonant chains, the resonant chain systems that formed while the gas is still around. And the blue curve is what happens after the gas goes away and those chains explode. And in very simple terms, if you mix together the red ones and the blue ones, you can match the gray one because it's in between. And doing some statistics on this, you need about 95 to 99% of systems to go unstable after the gas goes away to match the period ratio distribution. And then it matches really well. And so the story kind of holds that most, maybe all, super systems went through a phase of this resonant chain existing, but most of them disappear, right? The gas went away, they went unstable, and the planets we see now were shaped in large part by that final collisional phase. And a few cases, once in a while, the resonant chain survives. And these are some of the coolest systems we got. So here, for example, is the TRAPPIST-1 system. Probably the coolest system that has been found so far among exoplanet systems. I don't think too many people will be upset with me for saying that. A system with 7 planets that are all roughly Earth size. 3 of them fall in the classical habitable zone. It's a super cool system, right? And part of what makes it cool is the resonant structure of the system, which actually allows us to understand a little bit more about how it may have formed, how its orbital dynamics work. And also the fact that it's a resonant chain means that the planet's orbits are super thin. And so if we're lucky enough to see one planet, we're probably going to see a lot of them. And that is the case. We see all 7 planets in transit around their star. All right, so that's the end of super-Earth system, of the super-Earth section. Let's move on to giant exoplanets. And so again, here are some of the constraints. I'm going to go again through some of the constraints that we have for giant exoplanets. Here's the radial distribution of gas giants, where there are, again, a few hot Jupiters close to the star and a lot more distant Jupiters past around 1 AU, right? So Jupiter is sort of at the outer edge of what's currently within this distribution. But, beyond 1 AU is where most giant exoplanets are found, right? The mass distribution is such, this has been found, this particular plot is determined by a microlensing technique. Basically, the mass distribution is such that there are fewer, we're quite confident there are fewer more massive gas giants than less massive ones. And so for every Jupiter, for every some number of Jupiters, there's one super Jupiter and so on. And there's a lot, it turns out there's a lot of ice giant mass planets out there. Things are roughly Neptune or super Earth mass type planets out there, but not as many Jupiters. The eccentricity distribution is again a key constraint, exactly how stretched out planets' orbits are. That we talked about a little bit last time, and we'll talk about more in a moment. Another constraint comes from the giant planet metallicity correlation. This was one of the first correlations found related to exoplanets, and specifically to giant exoplanets, since that was the sample that was being analyzed early on. And basically the idea here is the x-axis is the metallicity calibrated to be to iron of given stars, and you can see that the fraction of stars that have giant planets increases as a strong function of the metallicity. And so something about having a lot more metals, maybe more of the material to build planetesimals, for example, helps to form giant planets. So now let me go through formation models for giant planets. There's kind of two main ones. The predominant one is the core accretion one, but first I'll talk about the disk instability idea. So the disk instability idea basically requires that some region in the disk is dynamically unstable. It means it wants to kind of clump and form a gravitational clump. And there's a simple way to formulate this using a Toomre criterion. All right, it's not too important. If you want to go in the details, you can. But very simply, it can be quantified like that. And simulations of gravitationally unstable disks make beautiful pictures. When I was in grad school, there were people doing this kind of thing. And every group meeting, they'd show these simulations, and I was super jealous because they're super cool. Anyhow, so as you can see, the formation of giant planets by disk instability is like beautiful. It really looks awesome. Now, does it really happen in real life is the question. Yeah. According to models, it should happen when, for systems that have very massive disks, and in those cases, it should happen in the outer parts of disks. Okay? So you can see in this plot, the unstable part is in the outer parts of disks as long as there's sufficient mass. That's where instability may happen. Right? And what remains unclear is whether, even if a planet forms by instability, whether it would stay there. And so some studies suggest that even if clumps, in the outer parts of systems go unstable, form, what looks like it may become a big Jupiter out there, you already need to have a lot of mass in gas out there. Gas is what drives orbital migration. More massive disk causes faster migration. And so it's quite plausible that most of the time a clump forms, it actually migrates in quickly. And so what this plot here is showing are examples of that type of calculation, of planets forming out at 100 AU, but migrating inward very, very quickly. Now let's move on to the core accretion model. So the core accretion model is kind of motivated by the general idea that we think that giant planets have cores that are a little more massive than Earth and a bunch of gas on top of them. So if they form from the inside out, you'd expect them to form a core first and then pile some gas on top. All right, that's the general concept. All right, so you can see the word core accretion. You grow some core and then accrete some gas. That's the general idea. I think that these days it's more kind of reasonable to think of it as the core migration accretion model, because you can't do this in a real context without thinking about migration, because cores are the right mass to migrate quickly, and we know that they have to form within an environment with lots of gas, because the gas is what's going to make the gas giant, and the gas should also drive migration. And so migration is a key part of the puzzle now. Now here is a diagram just kind of showing the cartoon, a very simple calculation of kind of the standard core accretion model. And so I labeled some different parts of this. And so in terms of the processes going on, early on planetesimals must form. Then very quickly, probably via pebble accretion, largest planetesimals have to grow into giant planet cores of several Earth masses. then the growth would presumably shut itself off by reaching this pebble isolation thing that we talked about earlier, where a pressure bump exterior to the growing core's orbit would trap pebbles and kind of stop them from growing anymore, stop them from falling on the core anymore, I mean. After that, there's this kind of long phase of grabbing onto some gas from the disk. The core grabs onto some gas. It's got to wait for the gas to cool enough to kind of contract so that it can grab onto some more, and so on. And that process can be quite drawn out. It depends on the kind of the thermodynamics of that process. It can be a little faster than what's shown here, but it still is thought to be a relatively slow process. And then when the conditions are right, there can be a runaway gas accretion phase. It's usually thought to be triggered when the core mass is about the same as the mass and gas piled onto the planet. Then it can go runaway. And then very quickly the planet can grow from a, kind of a Neptune up to a Jupiter, and in the process carve a gap in the disk and so on. So this is kind of the general core accretion scenario. So then the migration part would basically be all along, as soon as the object was at least a few Earth masses, migration has to be accounted for. And so here are some growth tracks, a very simple analytical model of growth tracks, trying to take into account many different processes. And so starting from large planetesimals growing by planetesimals bashing into each other, then pebble accretion, and migration also. And so you can see these kind of different arcs, these different tracks forming there. Each track represents, kind of the seed of one planet started at a given distance. As the object got bigger, then it migrates inward. As it got large enough to undergo different phases of migration, you can see that the trajectory changes. What's interesting is that it always goes inward. And so in this kind of model, everything that formed inside of 10 AU ends up as a hot Jupiter. Right? There should be a zillion hot Jupiters according to this, or maybe just no large cores ever formed within 10 AU. It's kind of hard to understand. And so on a kind of a philosophical note, we could say well, if these processes are right, we have some idea of these different processes like pebble accretion and migration. How did Jupiter end up at 5 AU? Why do we have any giant planets that are on wide orbits, given that migration is kind of pulling them inward? And the truth is we don't know. But let me give you some possible answers to that question. So one is that, maybe Jupiter's core did indeed start off at 15 or 20 AU. And it really did grow and slowly come inward and end up stranded at around 5 AU where it is now. So maybe that really did happen. It's not very satisfying because what happened to all this stuff interior to 20 AU? Can there really only have been that little stuff closer in? Maybe there was. I don't know. Maybe migration is much slower than we thought, especially giant planet migration, because the part of the migration once the gap is carved in the disk depends on how fast the disk evolves. And if the disk has very little viscosity, then it evolves very slowly, and so that migration can be super slow. Maybe it got basically Jupiter migrated inward, but then this happened late enough in the game that the disk, as it dissipated, had already kind of started to be chopped into two by photoevaporation. So this image is showing kind of the dissipation of a disk due to photoevaporation. So if Jupiter was migrating in from the outside relatively late, it couldn't get past that barrier, that inner edge of the outer part of the disk. Or another possibility, again, is that it was Jupiter on its own would have migrated much further inward, but Saturn stopped this from happening, and the two planets together either stayed where they were or even migrated outward. And that's the basis of the grand tack model for the solar system that we'll talk about a little later. All right, now looking at the giant exoplanet eccentricity distribution. As we talked about a little bit in the past, we think that the kind of key process here is planet-planet scattering. And so this kind of simple cartoon is, showing two giant planets that form on concentric circular orbits. In time, their orbits kind of kick each other around and change shape a little bit. Here, after a time, their orbits cross, then they undergo a scattering phase, and one of them goes away, probably being ejected from the system, and the survivor has a stretched out eccentric orbit. And so again, looking at the giant planet eccentricity distribution again, we think that that scattering process is key for moving planets up in this diagram, up to higher eccentricities. Now, when should scattering happen? Like I talked about before, when planets, when two, say when the growing Earth, its orbit was crossed by a large embryo, that usually ends up in a collision. But when two gas giants, have orbits that cross, it seems to end up with something getting scattered out. So when does scattering win? And when does accretion win? And there's a very simple way to think about this, about scattering versus accretion that I'll explain now. And so there's a simple kind of requirement. You can imagine if a planet were to eject something, if a planet wants to kick something out of its host planetary system, how does it do that? It does it with gravity. What's the strength of the strongest gravitational kick a planet can give? Well, in terms of the velocity, the speed that it can give something, the strongest speed it can give is the escape speed from the surface of that planet. Okay? So if that planet can give a certain escape speed from the planet's surface, well, how does that compare to the escape speed from the system? Right? That's the key thing, is comparing those two quantities, the escape speed from a planet's surface to the escape speed from the system, at that distance from the star. And so if the escape speed from a planet's surface is larger, especially much larger, then it can easily give a gravitational kick that in one shot can eject something from its system. If it's the opposite, if it's much less, then it can't do that, and it will typically, it's very hard to eject things. And the ratio of those two quantities is sometimes called the Safronov number. And as you can see in this kind of very simple equation, it's just the ratio of the escape speed from a planet's surface to the escape speed from the system at that distance. And you can quantify it in a relatively simple way. For Jupiter, Jupiter's Safronov number is like, 10. Earth's is much small, less than 1. I don't have a number off the top of my head, but it's small, right? So at Earth, if Earth is going to bash into things, Jupiter is going to eject things, on average, right? Sometimes things do bash into Jupiter, and Earth can, in principle, actually eject things as long as it gives many, many small kicks to reach escape. But most of the time, Jupiter's dynamics are dominated by scattering and Earth by accretion. And I just said this, but you get the idea. Once again, high Safronov number, scattering, low Safronov number, accretion. And if we look at the giant planets that we know, we see kind of rough confirmation of this idea. And so the x-axis here is basically the Safronov number of a given giant exoplanet. And the y-axis is the observed orbital eccentricity. And what you can see is for Safronov numbers above 1, the eccentricities are much larger. And for Safronov numbers less than 1, they're much lower, on average, right? And so this kind of goes in the right direction, that scattering is dominating those high Safronov number planets and much less for the low ones. And it's a little bit tricky because what really matters is the Safronov number when the action is happening, not afterwards. And what we're seeing right now is afterwards. That's why it's not a perfect correlation. But the general idea still holds. And again, I'll show this movie again because I think it's a beautiful movie. As you can see, it's made by Eric Ford. So just the dynamics of what's really going on is when the orbits of a few planets change shape a little bit in time, eventually cross, here's a phase of multiple scattering, and then boom, one final very strong gravitational kick that ejects the planet. And again, the survivors tend to have stretched out orbits that are scars from this violent instability. All right, that's planet-planet scattering. And what's nice about this mechanism is it kind of fits nicely with a general conceptual picture. It's not just one planet forming, it's several, and how do they interact? But it also matches the eccentricity distribution really easily. So this plot here is just showing a really, really simple set of simulations without tweaking anything that match the observed distribution. Boom, my first shot, I didn't have to do anything. The one thing that is required here is that most systems have to go unstable. And so for this model to match the observed eccentricity distribution, at least 3/4, maybe more like 90 or 95% of all giant planet systems have to be the survivors of instability. And so that's kind of interesting. That means that our simple picture of systems forming and being relatively stable cannot work, right? So this is it's the key point. Just the idea of instability being such a universal process is really important. And we saw that instability was key for the super-Earth population. After the gas disk went away, the super-Earths bashed into each other. They were in a very, very low Safronov number regime, so they bashed into each other, they didn't scatter. The same kind of thing may be going on with the giant exoplanets, where when they go unstable, they scatter. And what we see there is the evidence comes from the eccentricity distribution. And what's cool is that, we don't talk about it a ton, but for every time you see one of those instabilities happen, one planet goes away or more, gets ejected into interstellar space. What happens to those? Well, they don't just disappear, they become free-floating planets, they cool down, they're very hard to detect, but if you look in the right place or in the right way, you can find them, and there's more than 100 free-floating planets have been found to date. Most of them are kind of Saturns or Jupiters because they have a bigger signal, they're easier to see. But actually with microlensing, free-floating planets as small as, a little bit more massive than Earth have been found, which is pretty cool. So this gets to the summary of the exoplanet formation models. So for close-in super-Earths, in situ growth is not possible, but migration seems to be unavoidable, and this general idea that migration into resonant chains followed by a phase of instability that leads to collisions, that we sometimes call breaking the chains, can work really nicely to match the period ratio distribution. And some uncertainties come from, for example, where do the first planetesimals form? Are those planets that are migrating and then bashing into each other rocky, or are they mostly icy? Those are questions that we're asking now. We don't have great answers to. But the general physical processes involved seem to work pretty well. All right, so in terms of gas giants, the disk instability model can work pretty well, at least for wide orbits, very massive planets. It's unclear whether those are going to survive or not. The core migration accretion scenario can work pretty well. One difficulty is keeping planets on wide-ish orbits. And the planet-planet scattering model works really well for matching the orbital eccentricity distribution. As I mentioned before, it really kind of emphasizes the idea that dynamical instability is probably a really important process in planetary systems in general. Now we'll move on to the final part, which is about the solar system. So kind of here's a very rough outline of what I'll talk about. I'll talk again about the constraints and how we use those to kind of put together a very rough timeline for when we think things happened in the solar system. Then I'll describe the classical model, which was really the standard model of solar system formation until recently. Then we'll talk about alternate models that do a better job of matching constraints. And I'll briefly talk about the origin of Earth's water at the end. So solar system constraints, again, these are the planets we got. Any model that wants to reproduce the solar system has to produce something that looks roughly like this at the end. Kind of the key things are things like the planet's masses, their orbits, their compositions, and so on. There's the asteroid belt that is the leftovers, stuff that did not get incorporated into the planets. The asteroid belt is very interesting in that it has a very large region of orbital real estate between the orbits of Mars and Jupiter, yet it is mostly empty. It only contains less than 1,000th of an Earth mass in this very big region. And so the fact that it's mostly empty is actually a pretty big constraint on solar system formation models. And it's very, models are not at the point where we're trying to match every little bump and wiggle in the distribution that we see. But there's a few key things that we do have to match. Things like the rough compositional distribution, where the inner part of the asteroid belt is dominated by relatively dry stuff. Things like S-type asteroids that we think represent ordinary chondrite meteorites. The outer part of the belt is much wetter. It's dominated by C-type asteroids that we think are matched with carbonaceous chondrite meteorites that have some water. And so these kinds of things, models still have to match these very rough divisions between the belt and the orbital distributions of the belt as well. Basically, the asteroid's orbital eccentricities and inclinations are both pretty excited. So you can see the eccentricity on the top and the inclination on the bottom. These are only for the biggest asteroids. But you can see their orbital eccentricities go from 0 to 0.2, 0.3, and their inclinations from 0 up to more than 20 degrees. Right? Compare that with the planets. All the planets' orbits are within a few degrees of the same plane, and none of the planets has orbital eccentricity anywhere near 30%. So their orbits are very exciting. There's also a lot of constraints that come from meteorites, right? These kind of rocks that came from the asteroid belt that are real pieces of leftover stuff from the formation of the planets. And there's a lot of different kinds of information that can come from meteorites. And I'm not going to talk about it in great detail. I'm not a meteoriticist. But one thing that can come from meteorites, for example, are ages. And so, for example, the ages of meteorites, the isotopic ages, can be used to kind of set very rough timelines for things that have happened. And so the oldest solids in the solar system are these things called CAIs, calcium aluminum rich inclusions. And so those are often used as basically time zero. When we talk about the chronology of solar system formation, we usually talk about, after a few million years, this happened or that happened. The time zero for that is generally is generally invoked to be CAIs. Right? And that's a thing that comes directly from meteorites. There's many other interesting constraints. So I'm just going to list a few other kind of key constraints that play important roles in formation models that we get from meteorites or from geochemical and cosmochemical stuff. So isotopic and compositional analyses of rocks. All right. So one interesting one is hafnium tungsten isotopes. And those actually constrain when Earth's core formed. And so what's interesting there is basically, as you can see, depending on the slope of the curve there, in terms of this isotope space, they correspond to certain ages. And so some asteroids, some forming objects in the solar system, if they form cores, they form very early. Yet for the Earth, its core probably didn't form until at least 30 million years after CAIs. And more like, possibly even 50 or 100 million years later. And so that's a kind of key piece of information. The idea that Earth had this kind of long, late accretion phase, this late phase of giant impacts, comes from this kind of chemical constraint telling us that Earth's core probably didn't form immediately. That same type of analysis suggests that Mars, the same analysis done on Martian meteorites, suggests that Mars actually grew fast. And so in contrast with the Earth, Mars's growth was done within 5 or 10 million years. And so this plot is basically showing growth curves that can match Mars's isotopic measurements. So Mars did finish growing within 5 or 10 million years, whereas Earth wasn't finished for another 30 or 50 or 100 million years. And the event that we think, reset this or set the hafnium tungsten clock on Earth, the final core formation event on the Earth, is the last giant impact between the growing Earth and another planetary embryo, and we think it was the one that created the moon. So here's an animation of one version of the moon forming impact. And so what you can see here is, boom, there's a big impact with this other object. The impact can happen repeatedly and usually ends up kind of spreading out this disk of material. And kind of the reaccretion of material within that disk of stuff can form the moon, basically. And there's a lot of different studies of this process showing that there's several different flavors of moon forming impacts that may possibly explain our own moon. There's a model invoking multiple smaller impacts. There's multiple models invoking a very fast spinning Earth. There's other models that propose that this kind of giant disc-like structure called a synestia of rock vapor was created afterwards. And so the details of this are still being thought of, right now. But it's pretty well agreed upon that the moon formed out of a late impacts anyway. And so we can kind of put these pieces together right now into this very rough timeline for how fast we think things came together. And so this is what I call a kind of a cosmochemically inferred timeline. All right, so within this cosmochemically inferred timeline, within a few 100,000 years of CAIs, large planetesimals were already forming, some that were big enough to even differentiate. Within a few million years, there were large planetary embryos, and we have good evidence for that. And then kind of the general picture is kind of similar to what I had shown you before, that the final late accretion, late sweep-up phase and kind of late stage accretion, final giant impact phase lasts for 30 to 100 million years. And that's kind of the general timeline we have for the growth of the Earth and for the terrestrial planets. And so this goes back to what I showed you last time, this very simple picture of trying to put together all the puzzle pieces for how we think Earth grew, how we think Jupiter grew. And so I'm not going to go through each one and have them all pop up at separate times like I did last time. But you can see, this is kind of the general cartoon version of the growth trajectory that we have in mind for Earth and Jupiter. So now let's look in a little more detail. How do we build models that actually match the inner solar system? So again, what are we really trying to match? I keep coming back to this because getting the constraints really carefully defined is of great importance. So the inner solar system, what does it consist of anyway? There's about 2 Earth masses worth of rocky planets. Then there's less than 1,000th of an Earth mass worth of asteroids. And if we go into a little more detail, there's things like the numbers and masses and orbits of the rocky planets, the growth time scales, at least for the Earth, compositions, isotopic ratios. For the asteroid belt, there's the total mass, this dichotomy where the inner belt is more S-type, the outer belt is more C-type, and the orbital distributions of these things. And so let's look at the classical model. This was initially pioneered by George Wetherill, and starting in the 70s, I believe. And it's still being worked on now, even though, as you'll see, it's been kind of left behind. The classical model makes a kind of a key assumption here. And the assumption is this, that there are various lines of evidence, especially from the fact that gas disks around other stars only last for a few million years. So we think that Jupiter and Saturn formed fast, within a few million years. Whereas we have this evidence from things like hafnium tungsten isotopes that Earth's growth didn't finish for another 50-ish or 100 million years. So based on that, we might think that the final stages of Earth's growth were affected by the gravitational perturbations from the gas giants. And the kind of key assumption made in the classical model is that these can be treated as separate things. So if we want to study the growth of the terrestrial planets, it's all right if we don't know exactly how the giant planets form. Let's just plop them in there and see what happens, right? That's kind of this key assumption. Those can be treated separately. And as we'll see later, that really kind of undoes the whole model. But here is an animation of the classical model. And so what you're going to see here in this simulation is the y-axis is orbital eccentricity, the x-axis is orbital distance, semi-major axis, and the color, each dot that you see here is basically a small growing planetary embryo. And its color represents its water content. So red means basically dry, dark blue means, it has some water, about 5% water. And so when the color of something changes, it means that there's a mixing between objects that start off in different zones. And as you can see at time 0 here, Jupiter's already, we assume it's already formed. And so time 0 here corresponds to kind of when the gas disk went away. So relative to CAIs, time 0 here is more like 3 or 5 million years after CAIs, once the gas disk went away. So I'm going to start the movie, and you can see things get excited pretty quickly. They get excited from the inside out by mutual gravitational kicks, and from the outside in by kicks from Jupiter. And you can see within 10 million years, there's already some pretty good sized rocky planets growing. And that one at 1 AU grows into a pretty decent Earth analog. It's already there. And you can see right now its color is changing. It gets blue and green because its feeding zone has been expanding. And it's, it has some collisions. It's been impacted by objects that started off out in that zone that started off blue or so. Okay? And so its feeding zone expanded basically to include objects that included water. And within 100 or 200 million years, this kind of simulation, the accretion phase is wrapped up. And in this case, we formed 3 terrestrial planets. The 2 inner ones are decent analogs to Venus and Earth. The third one is a really bad analog for Mars. And then there's some leftover junk that you can kind of squint and say, it looks like the asteroid belt. And if we do this kind of exercise many times, then you get a distribution. And so this plot is showing one such distribution. And it's kind of an ugly plot. I should remake this. Or I should use a different one. It's not important. All right, so anyhow, this plot is showing the outcome of many simulations. It's showing the mass of a planet on the y-axis and the semi-major axis, the orbital distance on the x-axis. And so the squares are the actual planets, and the gray symbols are the simulated planets. And when they have those big horizontal error bars, those are their eccentricities. And so what you can see is, there's a lot of gray things near Earth and Venus. Right? That's good. But Mars it's not really well appreciated, but Mars is tiny. Mars is only about 1/10 of Earth's mass. And the planets that form around Mars's distance in these simulations tend to be a lot bigger. They tend to be half an Earth mass, or even an Earth mass. They're way bigger, way more massive than the actual Mars. And this is what we call the small Mars problem. And it's really the Achilles heel in the classical model. The classical model systematically messes up Mars. It can't naturally form planets where Earth is big and Mars is small, right next to each other. Sometimes Mars-sized things do form, as you can see. They form in the asteroid belt where there are no Marses. But planets that are right next to each other tend to be similar in mass, not have an order magnitude difference in mass. And that's really what sinks the classical model ship. So it's too bad, but Mars has really sunk that ship. We're not trying to match the outer solar system. Let me say this again. So now let's talk, we're going to zoom out and look at the outer solar system for a moment, because we're going to put in some more pieces before we revisit the growth of the terrestrial planets. Okay. So now we're going to go back and look at the outer solar system. And you see I've included some random pictures from movies as we go, but you can ignore those. All right, so matching the outer solar system. As we talked about for giant exoplanets, we think that instabilities are basically ubiquitous in giant planet systems. And it turns out that we think there was actually an instability in our solar system too. All right? And this instability was much wimpier than the one typically among, that characterizes giant exoplanet systems, but it still is key for the story of our own solar system. And so here's the idea. It's sometimes called the Nice model because it was developed in the French town of Nice. The idea is, to match the giant planet's current orbits, one way to do that is to imagine, early on, while they formed in the gas disk phase, it makes sense that they would have migrated. And kind of like in the super-Earth formation model, it makes sense that they might have gotten trapped in resonances. In any case, their orbits should probably have been closer together. But, there are some leftover comets and stuff further out there. So there probably was some leftover junk, some leftover icy junk analogous to the early asteroid belt, just beyond the planet's orbits. And so in this model, what is invoked, the idea is that let's assume that the giant planet's early orbits were more compact and there was an outer belt of stuff, okay, and see what happens. And what happens is that interactions between the growing planets and this stuff lead to an instability in the planet's orbits and clearing out of most of that stuff. So here's kind of one animation of this process. As you can see in this animation, there's actually 5 planets. There's 5 giant planets. One ice giant is ejected right there. And 4 planets survive on orbits that are very close to their current ones. And so the animation is going to loop back so you can see it again. What you see is they start off on more compact orbits that are nice and resonant. Makes sense from a how they form point of view. After a certain amount of time, they went unstable, got rid of all, the vast majority of that outer disk of planetesimals, and the giant planets landed on or close to their current orbits. And this model matches the giant planets' orbits really nicely. And so the reasons why this model is favored are because it can explain a lot of different aspects of the solar system at once. It can explain the giant planets' orbits. It can explain a whole bunch of things about the distribution of small bodies in the solar system, like the inclination of the Trojan asteroids. It can explain the irregular satellites of the giant planets. It can explain the orbital structure of the Kuiper Belt. It can do a lot of things. Okay, so we like the idea. What about the timing? Well, when this model was developed in 2005, it was developed to explain, in part, what was called then the late heavy bombardment, or the terminal lunar cataclysm. Right? The idea being that there was a spike in the bombardment on the moon, and so recorded in the crater distribution on the moon. And so the model initially invoked kind of this slow evolution at first, with then a late instability. And so this diagram is showing the early evolution, basically the evolution of kind of an early version of this model, of the Nice model. And it could work. There were a few cases that worked nicely where there was a very late instability, but it was very hard to do. There's no natural trigger for things that wait so long. It would be like, basically an instability like this would be like someone cuts you off while you're driving to work, another car cuts you off, then you wait 2 years and then you yell at the person, right? It doesn't work. No one does that. It doesn't make sense, right? And so a late instability like that is very hard to understand, right? And you could put in the right parameters, and once in a while it worked, but it was not very satisfying from a dynamical point of view. What is new is that there's some new constraints, basically reanalysis of crater counts, reanalysis of many different aspects that were originally used to invoke this kind of late spike in the bombardment, have been now reanalyzed. And actually, by adding new constraints, now we think that the instability must have happened early. And so how early? Well, it absolutely cannot have happened later than 100 million years after CAIs. It could happen any time earlier than that, according to some studies. According to others, it had to be earlier than about 20 million years. Basically, it could have been any time, as long as it was relatively early. And so the solar system timeline from back in the day went like this, right? There was a gaseous protoplanetary disk for a few million years after CAIs. The disk went away after a few million years, like I said. Jupiter and Saturn had already formed within that time. Mars was actually mostly formed within that time. Earth, however, had at least one big impact later, maybe 100 million years later, and then this big instability happened after that. So that was the solar system timeline from 5 or 6 years ago. Now, the current timeline has all these things much more overlapping, right? Things happening sort of at the same time, and which is kind of interesting. There's some constraints that haven't really changed, like the timing of the moon forming impact or the length of the gas disk phase, but the timing of the instability has changed a lot, and that's kind of the key one that mixes things up. Oh geez, I forgot to talk about this part. Gas disk phase, giant impact phase, sweep up phase. I'm going to talk about alternate solar system formation models. And so these are a little weird. These are like taking little pieces of a puzzle and arranging them into some structure you wouldn't expect, because who would do such a thing? Anyhow, I just do this kind of to make it fun. The eyeballs are from hydrodynamical simulations. The nose is an observed asteroid. And the smiley face are images of Jupiter. So, just so you know. Let me go through now different scenarios that we got for explaining the growth of the terrestrial planets. Okay? So here's the classical model in cartoon version. So again, we're trying to reproduce, there's a couple Earth masses and stuff in the terrestrial planet forming zone, 1 or 2 Earth masses in the asteroid belt, then a bunch more stuff further out to form Jupiter. And here's what the classical model typically produces. It produces Earth and Venus that looks fine. Mars is way too big, and the asteroid belt contains some Marses, and it's usually way too populated. It really doesn't work. Right? The Mars problem messes this all up. As of today, there are at least 3 possible solutions to the small Mars problem. And so I'll talk about each of them for a few minutes. They're the low mass asteroid belt model, the Grand Tack model, and the early instability model. So let me just kind of go through the ideas behind each of these. So the low mass asteroid belt model kind of makes an assumption, which is that from the very start, there was just not that much stuff in the asteroid belt. And that explains why there's, got some stuff to form the terrestrial planets, then very little stuff, and then stuff to form the giant planet cores. And there was just not much in the asteroid belt. It was low mass from the start. This feels kind of weird. Why would you say such a thing? Well, one way to justify this is to look at, images of planet-forming disks around other stars. They often show these kind of ring structure. And as we talked about, the building blocks of planets are planetesimals. Planetesimal formation is very sensitive to the local conditions. And so you can easily imagine, well, in that bright ring where there's a pileup of dust, maybe planetesimals are forming there. And in that other ring that's, where there's a little bit of a deficit of dust, there's no planetesimals there. So maybe that's why, that happens. So, you can see that simulation of the streaming instability forming planetesimals, and this other simulation of a ring of planetesimals forming within a disk model. So maybe planetesimals tend to form in rings, and that's a justification for these starting conditions. Anyway, if that were true, then we can actually do things that look pretty good, because the evolution of a ring of planetesimals is such that big planets form within the ring, like Venus and Earth, and small planets get kicked out of the ring, like Mars. And so it can actually explain the distribution of the rocky planets really well. It's kind of cool. So in terms of the asteroid belt, though, like I said, the asteroid belt's not completely empty. The asteroid belt could still have been filled or populated from 2 different places. As the giant planets form, they would have naturally kicked some stuff inward. Some of that gets trapped in the asteroid belt. Some would even go past the asteroid belt towards the growing terrestrial planets. And also, as the terrestrial planets are forming, they do kick some amount of stuff out into the asteroid belt too. So even starting from an asteroid belt that was perfectly empty, you would still refill it from the outside and the inside. And so this kind of general idea can work pretty well. The second model is the one that's the best known because it's been around for 10 years now. It's called the Grand Tack model. And it's based on the idea that while Jupiter on its own migrates inward, Jupiter and Saturn together can, in some cases, migrate outward. And so here's kind of the cartoon version of the general idea. So here's a very simple argument of what we think Jupiter might have been doing as it grew. So you can see it kind of started off somewhere out there as a big planetesimal, grew by pebble accretion. It kept getting bigger, and it started migrating inward. First really fast, and then kind of slowed down. It carved a gap and was migrating inward slowly. And left on its own, it would just keep going inward. But Saturn was doing the same thing a little further out. It started getting bigger, migrated inward quickly, and caught up to Jupiter. And as we saw, that doesn't mean it's going to collide with Jupiter. It means it's probably going to enter in resonance. Probably the 3-2 or 2-1 resonance if you want the details. And what's neat is there's a neat hydrodynamical effect where 2 giant planets that are trapped in resonance, where the inner one is more massive than the outer one, can migrate outward. And this works in a certain range of conditions that are plausible. And so Jupiter and Saturn may well have kind of just migrated outward. And they could keep going more or less indefinitely until they either reach a special spot where the disk changes shape or until the gas disk starts to go away. And then the assumption here is that Jupiter would have been stranded kind of close to its current orbit at around 5 AU or so. And a key thing that's really kind of put in by hand is that Jupiter's turnaround point would have been at around 1.5 AU, which is pretty reasonable. That's where a lot of giant exoplanets are found, so it seems pretty reasonable. Here is a very simple simulation of the Grand Tack model. And so what's happening here is basically there's a disk of green planetary embryos and red planetesimals and Jupiter migrates inward and then turns around and goes back outward, right? And what's left is kind of, we went from a disk into a ring. And what happened is in simple terms, the conditions of that ring of planetesimals from the low mass asteroid belt model was created by Jupiter migrating inward then outward. And so that's why this model naturally produces small Marses. It works really well. The third model is the early instability model, and it's built on the idea of the Nice model instability happening early. And so as we talked about just a moment ago, we're pretty confident that this instability happened, but it probably didn't happen so late as we initially thought. It could have happened any time. And so in this model, if it's going to influence the terrestrial planet's growth, the instability must have happened very early. And so that's the assumption here. And so why would it happen early? One possible trigger, actually, a new idea, is that as the gas disk dissipated, you can see that the gas disk gets chopped in half, and as it photoevaporates, the outer part goes outward, and there's this kind of inner edge of the outer part that sweeps outward. And that inner edge can actually trigger instability. And so here's this kind of a simple demonstration of that dotted line as it goes outward, dashed line as it goes outward is the inner edge of that outer part of the disk, and it triggers the instability as it sweeps past the planet's orbits. And so maybe that was a trigger. That's one plausible idea. In any case, an early instability of the giant planets has the effect of really efficiently clearing out the asteroid belt and also stunting Mars's growth. And so in this simulation, what you can see is, you see snapshots in the growth of the planets, of the whole system going from very close to the sun all the way out. And after the end of the growth phase, the fourth panel down, the planets don't perfectly match the terrestrial planets, but you can see that the outermost terrestrial planet is much smaller than the next one in. And so it matches the Earth to Mars mass ratio really nicely. And in a statistical sense, it matches the planets really well. And so right now, there's three kind of plausible solutions to this small Mars problem. But they each have their own little issue. So for the low mass asteroid belt model, the issue is basically, are the initial conditions realistic? Is this idea of rings of planetesimals, does that really make sense? For the Grand Tack model, it's actually the outward migration mechanism. When you take into account the growth of the planets at the same time as the migration, does that really work? And for the early instability model, it's, when did the instability really happen? If it happened too late, it can't have done anything. If it happened really early, then it had to do something. And of course, there's some other new developments. I'm not going to go into detail on this. The image on the left shows that new ideas for when planetesimals formed in different parts of the solar system. So maybe the initial conditions for these models need to be revised. The image on the right shows a new idea that just came out this year that invokes pebble accretion for the terrestrial planets themselves. And so that's currently being thought of now, whether that could make sense in the context of the rocky planets. Okay, so now let me talk about the origin of water on Earth and other rocky planets. So, like in Jaws and such. So what are the constraints here? Well, all the water on Earth's surface is kind of what we consider one ocean. And if we look at what's in the mantle, there's a debate about exactly how much water is in Earth's mantle and the core. But assuming there's a few more times that Earth's surface water in the mantle and the core, the total amount of water on the Earth is still only about 1 part in 1,000. So we often talk about Earth as being this pale blue dot, and we do have a lot of water on the surface, but Earth overall is a pretty dry planet. So where did it come from? Well, we can look at small bodies in the present day solar system, and as you can see, there's the farther you are from the sun, the more water is typically contained in leftover bodies. These objects like different types of asteroids or comets. Okay? So it's natural to think that those are possible sources. In terms of the chemical signature, kind of the fingerprint of Earth's water can be thought of as its deuterium to hydrogen isotope ratio. And so here's the D to H ratio of Earth as compared with other bodies in the solar system. you can see that the giant planets, and we think the sun and even the sun, the planet-forming disk, had a D to H ratio that was 6 or 7 times smaller than Earth's. Basically, different types of meteorites, especially carbonaceous chondrite meteorites, have D to H ratios that match Earth's value really well. Most comets have values that are quite a bit higher, although a couple comets do have ones that match. Yet, even though some comets match Earth's D to H ratio, none of them match other isotopes, like nitrogen especially. So I won't dwell on this, but this means that comets are probably not a great candidate. So how did Earth get its water? Well, in this kind of very simple cartoon picture, we think that, for Earth to be mostly dry, it had to have formed inside the snowline, right, where the temperature is too hot to use ice as a building block. So we think that's where Earth formed, interior to the snowline. Then, in the classical model, if you think of this curve as kind of the feeding zone of the Earth, then in the classical model, that's that movie where Earth was changing color as it went. Earth changed color and got some water because its feeding zone extended beyond, to include objects that started off beyond the snowline. Right? But we don't like the classical model because it screws up Mars. And so in these other models, like the Grand Tack or low mass asteroid belt or early instability model, it would have been a little different. Earth's feeding zone would have been smaller, more constrained, but it would have had this kind of polluted effect. So most of the stuff that went into the Earth would have come from pretty close by, with a tail, a very small amount of pollution from stuff from further out. And dynamically that makes sense, and also chemically that makes sense, because then the isotope ratios of Earth's water would be the same as, for example, the isotope ratios of objects that were implanted in the asteroid belt by the same dynamical processes. All right, so one might wonder, well, if we want to imagine other Earths, is there an ideal amount of water to have on a planet? Well, planets that are really dry are bad for life, at least life that requires water. Planets that have a little bit of water can be good if they just have a little bit, but not too much, because water tends to enter within the greenhouse heating effect. And if there's only a little bit of water, it can avoid contributing too much to that. Obviously, there's Earth, and we like what we got on Earth. And if there's too much water, maybe that's too much. There's some people who have suggested that having very, very deep oceans can be bad because high pressure ices can form down low that would isolate basically the Earth's interior from the oceans. So that's a possibility. But here, now let me just kind of wrap this up. So here's a quick summary of the solar system formation models. There's the classical model that's suffered from the small Mars problem. There's alternate models like the Grand Tack, early instability, and low mass asteroid belt models. Then the origin of water on Earth, we think it's probably Earth grew mostly locally, but had this kind of pollution from stuff that came from further out. And now kind of what are the kind of key processes and unknowns in all this? Well, the key, kind of most important unknown of all is understanding the real structure and evolution of gas disks themselves. This is an area of study right now, and we really don't have the answer. Where and when planetesimals form is key. The balance between pebble and planetesimal accretion in different places is really important. We're pretty confident that migration and instability are really universal processes, but they enter in different places at different times in different types of systems. And one thing that hasn't been studied in great detail is the influence of external perturbations, for example, from other stars. That can really matter a lot, especially early on when planets form in clusters. And I have a couple closing thoughts just to give you, because I wrote these. So a couple of things to keep in mind as we go. So first, this kind of thing, I think exoplanet formation, solar system formation and stuff, they're cool, exciting fields. So I encourage you to jump in there. A key thing is to kind of understand these constraints. I mentioned constraints over and over again because that's where you can connect the dots to try to figure out new things by connecting constraints in a new way. And remember that no one is an expert at everything, and so planet formation encompasses many different fields, and so it's easy to feel like an imposter in all sorts of different ways. And so just remember that. It's a universal feeling. So philosophical thoughts. I'll just keep a few things. It's important, I think, to keep things enjoyable and fun while you're doing this. Another thing is that while many of us get really technical in what you study, it's key to keep coming up with new ideas, because that drives things just as much as big computers or telescopes or whatever you're doing. And as a wrap-up, feel free to contact me if you have questions or whatever. I put my email address there. And for additional resources, here are some, I'll just leave these on the screen. There's some review articles and stuff for you to check out. So I will stop there.